All right, welcome to chapter 5. In this chapter, we're going to introduce the concept of momentum, and then we'll use that to define the impulse in physical terms, of course. Then from there, we will look at conservation of momentum and how it can be applied to situations such as the description of collisions. All right, so a big part of this chapter is going to look at collisions between objects and different types of collisions and how to describe them. So before we can get to this, we are going to define momentum in this video. If we want to think about momentum conceptually, we usually talk about inertia in motion. All right, so these are two topics that we've covered a lot so far in previous chapters. And so if we actually try to quantify this, remember that for inertia, we usually said that we could quantify that using the mass of an object. So somewhere in the definition of momentum, we're going to have the mass of the object. And since we're looking at inertia in motion, we need a quantity that is going to describe the motion of the object, and we're going to use its velocity. By definition, the momentum is simply going to be the mass of the object multiplied by its velocity. And so if you want to look at this in terms of symbols, so again, mass times velocity. I forgot to turn on the pen. All right, here we go. So mass times velocity. All right, so this is what we have over here, mass times velocity. And remember that velocity is a vector quantity. So as it turns out, momentum is also going to be a vector quantity. In terms of the direction of this momentum, you can see that it's actually going to be exactly the same direction as the velocity vector, because we take the velocity vector, multiply it by a scalar quantity, which is the mass, but that mass is always going to be positive. So we know that the momentum is always going to point in the same direction as the velocity. And remember, because it's a vector, we need two pieces of information to be able to describe it fully. So the direction, which is given by the direction of the velocity. So where is our object going? And the magnitude, which is going to be given by the mass times the magnitude of the velocity or the speed of the object. So you can see that in order to get a large value of the momentum, we can be looking at an object that would have a large value of the mass or a large value of the velocity, or both. But you can also see that if we are considering an object which is very tiny with very, very little mass, it's going to be harder to give it a large momentum. And so why are we combining these two things? Why are we multiplying the mass of the object by its velocity? What exactly are we going to be describing here? So I already hinted at the fact that, you know, we're building this up so that we can eventually talk about collisions. And before we can get to this, so just picture that if you're are looking at two objects that have very different masses, so usually I like to look at, for example, an elephant and a fly. We could have them collide, but for now you can also just think about if you have an elephant charging at you versus a fly moving at the same speed. You know which one is going to be harder to stop, right? So same thing if you're comparing a large truck and a small car. Essentially, the object that's going to be more massive, so the truck, for example, or the elephant, if if all of the objects that you're considering are moving with the same speed, the more massive objects are going to be have a larger momentum, and because they have a larger momentum, we're going to have a harder time stopping them. And that's the idea we're trying to convey. That's kind of the picture that we're trying to get to, and why this quantity is going to be useful. Now, if you look at object with different speeds, however, so you could be looking at a car again versus a truck, but you could have a very slow truck, and as it turns out, a car with a lot less mass, but that would be moving very, very fast, may actually have more momentum. All right. Something to see from the definition is that if you have something that is not moving at all right, so it doesn't matter if it's the car, the truck, the elephant, or the fly, if they're not moving, their momentum is going to be zero, because their velocity is going to be zero. So they're not going to have any momentum at all. So really quick to practice on doing a quick calculation using the definition. Let's take a look at a 1,000-kilogram car driving along a street at 15 meters per second. What is going to be the momentum of the car? So I would encourage you to stop the video and try to figure out what that momentum is going to be. And then I'm going to go over the solution with you. And so, all right, so we said momentum is going to be the mass times the velocity. All right, so in this example, we're not given any information about the direction. So we're just looking at the magnitude of our momentum. So it's going to be our mass, which is 1,000 kilograms, times the velocity, or the speed. In this case, we're looking at the magnitude. All right, so that's going to be 15,000. And we haven't talked about the units. So you can see here that the units are going to be kilograms times meters per second. Okay, so 15,000 kilograms meters per second. So that's going to be the momentum for this car. All right, so that's by definition the momentum. We're going to be looking at eventually at how we're going to be using that, but just remember it carries information about inertia and velocity. So inertia in motion. And in the next video, we're going to start talking about the impulse. And then eventually we'll see how, in what condition we can claim that momentum is conserved. All right, thanks.